Is beryllium chloride polar? So, is beryllium chloride polar? So the reason why I call it beryllium chloride, as you notice, right, this is an example of an ionic compound, and because of that, the naming rules, right, we don't state, okay, like we not even need to, we actually do not state the fact that there's two chlorines there. We don't say beryllium dichloride, we just say beryllium chloride because it's a metal with a non-metal. And the question is asking if beryllium chloride is polar. With this, the best way to start, usually just drawing a Lewis Lewis diagram or Lewis body diagram or body dot a Lewis diagram. There we go. So the way to draw it is that we need to first figure out how many valence electrons are in beryllium and in chlorine. So for beryllium, because it's on the second column, we can say it has 2 valence electrons, but we can actually figure this out as well by drawing quickly something that we've been reviewing a lot lately, the electron configuration, which would actually start with helium, okay, and just be 2s2. So you can see here, because it has a 2 here at the top as a superscript, that supports that is its valence electrons amount. So beryllium would like to just give it up to be 2 plus, okay. Well, I mean, sorry, we don't need to know that. We just know that it has 2 valence electrons we have to account for, okay. And chlorine, we're going to approach it the same way. Quickly do the, I mean, it is on the 17th column, which means it will most likely have 7 valence electrons. But we always like to double check. So let's start with neon, and it would be 3s2, 3p5, okay, because we have the 2 here, sodium, magnesium, and then we count from aluminum 1, 2, 3, 4, 5. So yes, indeed, we have 7 valence electrons. So now there's 7 times 2, that is 14 in total. So to account for the valence electrons, we need to account for 16 electrons total, okay. So for this, because typically what we want to do is that the atom or the element with the least amount usually kind of situated in the middle. So we have beryllium in the middle, right? And we know that at least there is a single bond indicated by 2 electrons to the chlorines, okay? And now we add the chlorines there, and then we just kind of fill in the shells. At least we assume, because beryllium only had 2, so it doesn't really care about getting the rest, and chlorine wants to follow with the octet rule, right? And we kind of just fill in blindly, but then we count to see if we actually coincidentally accounted for all of them. So we do have 2, 4, 6, 8, 10, 12, 14, 16. So we actually accounted for all the electrons that BCl2 should have, beryllium chloride. So with that being said, now we just have to make sure that we actually did it correctly by factoring its the electron number, okay. So with that being said, beryllium prefers to have 2 because that is its valence electrons. We subtract how many lone pairs it has, which is 0, minus how many electrons in bonds, divide that by 2. So we do get 0 indeed. So beryllium is nice and satisfied. Chlorine, on the other hand, okay, we have 2, 4, 6 valence electrons and just 2 electrons in a bond. So with that, we also get, 0 plus, we also get 6 plus 2 over 2, 7. So 7 minus 7 is 0. So this is completely satisfied in terms of how it wants to situate itself. So now, because we see one bond, let's just redraw it. We have Cl, Be, Cl. So with this being said, actually, we have just an electron, we have a, I guess, bond number, electron bond number of 2, okay? And we have 0 lone pairs, at least on the beryllium, because that's what we're referring to. Not the chlorine, but the beryllium, the molecule in the middle, okay? So with that being said, this is going to be a linear, okay, linear electron geometry. And because of linear electron geometry, even though these two are indeed polar, as in these are the more, actually not even more electronegative, this is literally just chlorines are the negatives, well, not negatives, but chlorines are where the I guess negative charge will be situated, because you see all the electrons there, okay? But they literally, in terms of electronegativity, are pulling themselves equally to both sides, making that although we have ionic bonds, which does give directionality, okay, because remember the metal and non-metal, even though we have ionic bonds and they're quite big, because it's going to be 3.16 minus 1.57, so 3.16 minus 1.57, 1.59, which remember when we look at it, it's still a metal and a non-metal, so even though it doesn't hit the threshold of 2, it does still check off as ionic, okay? But the point being is that the chlorines are kind of like, in a sense, a perfect tug of war, to where they're pulling at each other, but no one will ever win, making BeCl2 in total a non-polar molecule, because it has a net, I guess, pull or charge of 0, okay? As in, there's, as you see here in this picture, everything balances out, so this is a non-polar ionic molecule. Okay, so let's see how we did. Yep, it is non-polar, and the way they explain it, exactly, they're symmetrical, as we showed through the linear electron geometry, and so they're non-polar. And yeah, so you see how I broke it down by first, you know, drawing the Lewis dot diagram. Sorry, that's because using this method you can actually see clearly if beryllium had any lone pairs, which it doesn't, and you can also see how the electrons are kind of like, I guess, situated between the two elements on the outside, showing how they balance each other out in total. Okay, this is correct. So now we're 646, moving on to question 7.